next thing on our agenda is our Extreme Environments panel. I'm going to ask my panel to please turn on their cameras. Erin, Charles, and Todd. Make sure we can see all their faces before we get going. So I'll talk a little bit before we start going is we're going to do this one just like the other. We're going to let all three speakers present their slides, and then we will take questions in the Q&A part. So please remember to put your questions in the Q&A. Erin, oh, she's trying to turn it on. I see it. Okay, well, I'm going to go ahead and let us get started, and we're going to start with Todd Schneider, and he's from NASA Marshall. So we'll let him sip his water, and then we'll let him go ahead and get started. Go ahead, Todd.
Great. Thanks a lot, Jamie. I really appreciate it. And thanks for the opportunity to speak today. So I'm going to go kind of quickly through this because it's a kind of a basics of the environment. And I want to give my co-panelists lots of time to talk about their portion of it. So let's march right on. So today I'm going to talk about vacuum environments and space environments, and certainly the lunar surface. Everything kind of begins with vacuum as the environment. And so I want to talk about some of the kind of basics of it, just give you an introduction, maybe bring forward a few concepts that if you're not used to dealing with vacuum, then it's probably very foreign to you. So I just want to plant the seeds for some of this. There's lots of great information online and in texts also. So there'll be plenty of opportunity to, find out more if you're interested or need to. So before I leave this chart, I have to say I love this graphic on the right, because it just shows the complexity of everything going on the lunar surface. And I think some of my my co-panelists will touch on some of those, so I won't steal their thunder, but it can be very complex really quick, but it all starts with vacuum. So I want to start with some basic vacuum units that are part of the nomenclature that are kind of a necessary piece of the discussion. And so TOR, T-O-R-R, continues to be a popular unit in the US. However, it is not the official SI unit. That is the Pascal. And so I have some kind of conversions and some things for you to see here. Let's start with 1 torr is 133 pascals. In the interest of kind of playing fast and loose to make some of these conversions easy, I often just round off the 1 torr is equal to about 100 pascals, and that can be helpful for sort of converting really quick. The Pascal is really derived from 1 Newton per meter squared, so it's an honest metric unit, obviously. We'll get into this in a second, but 760 torr constitutes 1 atmosphere of pressure, which we're under, on the surface of Earth. As a quick example, 1 10 to the minus 6 torr is equivalent to about 1.33 e to the minus 4 torr. So you're again, it's roughly a factor of 100. A really popular unit that you'll see in this presentation, I don't quite understand it, but it's a millibar, and a millibar is 0.75 torr. Again, if we just play fast and loose, you could make the case 1 millibar is about 1 torr. So the millibar is based on it's 100 pascals. So that's where it comes from. I did tuck in here that sometimes you'll see, especially on dial pressure gauges, the unit of a reference to mercury, Hg, and some of them show like 1 inch of mercury. That harkens back to when they were first making measurements of vacuum pressure, and you'll see it still sticking a little bit today. Real quick, if you're like, wow, there's a lot going on here, how do I know, what the conversions are, where do I find them? The good news is a quick, simple Google search, say torr to Pascal conversion, will pop up like a native converter, and so it's easy to figure those things out. So I want to just bring this forward because, again, if you're not used to dealing with vacuum, this may not be the most obvious thing. And I've tried to really simplify it here. There's a lot that could be said on it, but the basic point that I want to emphasize is on Earth we have atmospheric pressure, and that actually is also 14.7 pounds per square inch. And that could be significant when designing vacuum equipment, designing vacuum chambers, as I'll point to in a minute. And then as a reminder, again, 760 torr is 1 atmosphere of pressure. If you wanted to do it in Pascal, 1 PSI is almost 7,000 Pascal. So if I look on the left here and we look at ground-based testing, this would be where you have a vacuum chamber and you need to insert your instruments, your little mini rover, what have you. In this case, of course, we have atmospheric pressure pushing around all sides of that vacuum system, and you'll see most vacuum systems are cylindrical to take advantage of the natural sort of load shedding that comes with a cylindrical shape, a circular shape like that. So we spend a lot of our time fixing seals and things and making sure we're tight against, you see that atmospheric pressure pushing in on the chamber and trying to create leaks, into our systems. But on the lunar surface, so if we look to the figure on the right, we have obviously the opposite situation. We have a vacuum environment, which I'll talk more about in a second. And so the point is that if you have something that's going to be operating in the vacuum environment and it's a pressurized system or it's a capacitor that was created on Earth and has trapped air in it, that's going to want to come out because you see there's no equalizing force, there's no atmosphere to push against it. You have this vacuum, and so that trapped air is going to try and force against those walls. And so the point is you have to be able to withstand this kind of 14.7 psi differential, and that can be a challenge and certainly not something you want to ignore. So let's talk about the lunar environment and anchor it to some actual measurements. It turns out Apollo 12 and Apollo 14, I've just shown 14 here, did make measurements, tried to make vacuum measurements on the lunar surface. A few interesting things popped up. One is that they took basically a conventional vacuum gauge with them, very much like what we would use on Earth. It was obviously configured a little differently. So what they saw is routinely they would see, like, say 10 to the minus 8 torr. One of the things they noted is that just the presence of the astronauts and the EMU suit, which is generating a lot of water vapor for cooling and things, increased the local pressure, as did like the lander, and again, its cooling and environmental control systems caused these kind of localized pressure increases. They did note that when things would get cold after sunset, they would see pressures down as low as 10 to the minus 12, which is quite a significant vacuum. I'll classify that in just a moment. So one thing that I'm keen to tell folks remind folks is that yes, space environments and lunar environment is vacuum, but it's not empty, okay? And the LADEE mission, the Lunar Atmosphere and Dust Environment Explorer mission, kind of looked into some of these things. And you may be aware that there's a lot of descriptions going on to the exosphere that exists around the moon. So it's very much not like the surface of the Earth where we have this kind of high density atmosphere. But the point is that you have solar photons, solar wind particles coming in that can knock off gases, molecules off the lunar surface, chemical interactions. And of course, you have these impacts from meteoroids and from comets that will then evolve gas and is part of what constitutes the pressure, if you will, that's going to be part of that vacuum surface. So let's classify really quick. I thought it might be useful to classify the different vacuum regimes. This upper right table is a little hard to read, so I broke out a few interesting things here in a little bit easier to read format. And so if we start with low vacuum, that's roughly speaking about a millitorr, okay? High vacuum, then we would talk about kicking in at around 10 to the minus 5 torr to 10 to the minus 8 torr. And then ultra high vacuum, which we saw some of the situations on the moon, you could easily be considered into an ultra high vacuum or UHV environment versus HV. And that's really important, and I'll explain in a moment why we can test on Earth and justify, say, testing in high vacuum, even though our true environment might be ultra high vacuum. So before I get to that, again, this is for folks who just aren't used to dealing with vacuum environments. We talk about 3 different flow regime boundaries, and these occur as you're, say, evacuating a vacuum vessel. And we go from viscous flow to a transitional flow, and then finally molecular flow. Molecular flow is what we're going to emphasize and talk about more here, and it's really important. And again, it's something kind of not intuitive. Viscous flow is, as you might expect, where you are creating a differential pressure and particles, a lot of high density collection of particles are moving into your pump, okay, because you've created a lower pressure than, say, what's in the chamber at atmosphere. And then, of course, at some point you start transitioning, but what you end up with when you're into a high vacuum situation is you're into molecular flow. So now we cannot create this differential pressure to pump. Instead, we're relying on molecules to random walk their way into our pumps. And so we're in a truly rarefied environment here. And that's really important. And so if we try to quantify that, I think the metric of interest really is this idea of mean free path, which is the average distance that a particle can travel between two successive collisions with other particles. And so I think it's some helpful guides here in this table on the left. If you start at room pressure or atmospheric pressure, 760 torr, you have a whopping 68 nanometers before you've made two successive collisions for these molecules as they're moving through. So the point is that as we start evacuating our vacuum chamber, or as we encounter the lunar environment, now we get into mean free paths that are on the order of like 100 meters, okay?
Todd, I want to
So,
jump in for one second.
okay.
We have about 1 more minute.
For me, okay.
Yeah.
I'll
Okay.
whip through it. So again, this mean free path is really important, and this 100 meters means you're much larger than your vacuum chamber. And so when you achieve those kinds of conditions, it doesn't really matter if you're at 10 to minus 6 or 10 to minus 12 torr. No, because these mean free paths are quite long. And so I won't go into, this is a little bit more about this molecular density and so forth, and molecular flow. And again, a lot of this is compared with the mean free path is much greater than the diameter, say, of your vacuum vessel. And I think it's important to talk about the concept of outgassing. So every material has some level of outgassing. The takeaway here is not everything is really vacuum compatible and it's not good to use in vacuum environments. And so there's lots of materials that can be found on that. And it's important to know that, that not every material is the same in that respect. And so I just kind of want to conclude with a few examples of sort of vacuum systems and give you a feel for these general classes. And My contention is the ultra high vacuum, this UHV range, is really the domain of say, semiconductor manufacturing, where you have clean room environments and you have to take all sorts of measures to even get close to achieving those. And it's always done in a very small vacuum vessel. For the work that we're likely to do for this, environments group and for LSIC in general, is you might get into a chamber more like this size where you have a regolith bed in it. This is one of the ones we have here at Marshall, and so we were able to get to 10 to the minus 6 torr with regolith. So that's a high vacuum, very long mean free path. We're very much into molecular flow, and we could introduce the environments, electrons, UV, et cetera. So these are achievable. I have some other examples of that. And I'll just kind of finish with this picture. They're building quite a large system across the street from us, known as V20, and where they're going to have thousands of pounds of regolith in a vacuum environment, and where you could test much larger scale models. And I love this picture because somebody was ducking under the scaffolding here, and their head and neck got stretched out by the camera view. So I'll stop there because obviously I'm a little over on time. So thanks for your attention. I appreciate it.
Thank you, Todd. And if you guys have questions, because I see them in the chat, Todd, while the other is going, if you wanted to answer that question in the chat or the Q&A, that'd be fine. All
Okay.
right, we're gonna go with Erin Rezich. Oh, I hope I said that wrong. Rezich. I have a Southern accent. I say all words. I think right. Other people say it's wrong. Potato, potato. But we're gonna let her go. She's from NASA Glenn. Go ahead.
Perfect. I'm sorry, I gotta share my window again. And can we see it all right?
Yes.
Perfect.
Might want to put it in presentation view, but we can see it.
We good to go?
Yes.
All right. So as you said, I'm Erin Rezich from NASA Glenn Research Center. I started working here about 4 years ago as an intern, and I'm going to cover the topic of some regolith considerations for testing. And I've actually been messaging back and forth about vacuum chambers and regolith as we're doing this. So it's all, like we said, kind of ties together. And so to kick things off here, I think it's really important to kind of ground everything back into even though it's comparatively very little, what we do know about the lunar surface. And so if you really take the time and look through some of the Apollo photos of samples that they've collected, they're pretty amazing looking particulates that when you're testing like I do, or like probably many of you do, these physical characteristics matter substantially when you're testing on a large scale. So we just finished testing the Viper mobility platform in the Slope Lab at NASA Glenn. And so we tested in the GRC1 soil simulant, which is attempting to recreate the bulk characteristics of the lunar surface for traction purposes. So the lunar surface is crazy, right? We don't have atmosphere. And so because we don't have atmosphere, we have constant particle bombardment. We have lots of micrometeorite and even large meteor impacts on the lunar surface. And so this is a process that's referred to as gardening. And so gardening is the impact and mixing of lunar regolith, which is really the primary metamorphosis mechanism for the lunar surface in terms of the regolith itself. And so when a meteor impacts, you instantaneously melt some of the material, and then you get these glasses that form. And then they eventually cool. And so we call the glasses themselves are agglutinates, and they can oftentimes trap unmelted regolith particles in them. So you get these kind of lunar breccias, is what they're referred to as. So you can see up here in this upper right image, really strange shapes that are very fragile, but they exist because of these impacts. And so this is not a mechanism that we have here on Earth. And so creating these realistic scale individual particles is incredibly difficult. I mean, some people would argue they've gotten close. Other people would argue that those people are completely wrong. And so, but like we said, these individual particle sizes and shapes and makeups significantly change the bulk behavior. And so these are just some kind of interesting stats here about lunar regolith itself. So these are something closer to maybe a rock. We've got on the centimeter scale here, but then up here we've got millimeter scale. And the average grain size for our measured actual lunar regolith data is about 70 microns, which is incredibly small. And on top of that, we're looking at like 60% of the soil on average is this agglutinate format of particle. So again, something that's very difficult for us to recreate, but also at the same time significantly changes how we need to look at this, because agglutinates, because they're fragile, when you drive across the lunar surface, if you were to drive back over those same tracks, you likely have very different traction if you're crushing and smashing all these different little particles. So lots to talk about there, and if people have questions, and keep going. And so from those particles, you can see how they could be incredibly abrasive. So this whole slide is really just dedicated to that concept. This is an Apollo spacesuit from Apollo 12 from Alan Bean. And I think I really like these images that were shown in the report. So they took two primary samples. So they used, there's the American flag patch. So after the EVA, this is after they got back to Earth and everything. So they took a sample from what they're calling is the virgin material. Would be, it went to space, so it was exposed to the environment, but it wasn't exposed to the same dust environment as it was covered by this patch. So that's what they're comparing against. And then they use the shoulder and the left knee. So the left knee would, I mean, you can see from this image, is a heavily worked material, and then the shoulders, and then under the patch being virgin. And the actual EVA total time was under 8 hours. And so you can see pretty substantial damage in all of these, very small scale images after a comparatively very, very small amount of time. I mean, in terms of useful work done, when we start talking about excavation and large scale mining and stuff, 8 hours is not a terribly meaningful amount of time when you look at how mines and things are operated here on Earth. We're running 24 hours a day for sometimes, I mean, there's mines that have been running for 100 years. So abrasion itself is an incredibly powerful mechanism that lunar regolith is going to interact with many of our materials. And when you start talking about blades and buckets and all that, like these are incredibly hard materials in lunar regolith. We have lots of silicates and iron oxide, titanium oxides that are just abrading away at our digging materials. So this is certainly a factor. Wear is certainly a factor that needs to be taken into consideration when designing anything for the lunar surface, whether it be wheels or astronaut boots or things that cycle on the lunar surface. And so this is kind of one of my favorite examples. We find ourselves talking with the mining industry a lot and saying that, we know how to do a lot of things here on Earth, and that is very true. But we leverage gravity in pretty amazing ways, and we have for thousands of years here, and we just didn't really realize it. So the concept of taking, if we could literally launch this excavator to the lunar surface, you would have, this is what it weighs here on Earth. And so that results in a mass of this. And so even, first of all, this is an incredibly enormous launch mass, something that we are nowhere close to achieving and arguably could never achieve in one launch. Drawbar pull, so that you can calculate drawbar pull off of a vehicle's weight, effective weight in the environment. And so a rule of thumb estimate is the maximum amount of drawbar pull, which in this case would be like a digging force or a dragging force. So we're looking at 660,000 pounds. And that's all on Earth. So then if we take that on the moon and you do all the math, it basically comes down to you get 1/6 of the actual usable work effectively for the same amount of mass. And so to me, that reads as, I think there's a lot to learn from how we've done things here, and I don't think that we would throw all of it away. But the way that we have learned to design machines here on Earth for excavation and large scale mining operations 100% just leverages gravity that we have available to us. And so you can look up crazy machines. I mean, there's those massive bucket wheel excavators in Russia and things like that that are used to mine out coal belts. And those are only available to us because it costs nothing to make it bigger effectively. So gravity is a huge consideration. And there's some new literature coming out about how to test with gravity effectively. Obviously, you can try to do parabolic flights, but those are not always available financially, but they're also incredibly size restrictive. So people are looking at how do we develop maybe some scaling laws? How do we develop, can you use Buckingham pi theorems like you would in fluid dynamics and try to apply that to the gravity vector? Soil simulants like the one that we use in our lab, GRC1, was designed using geotechnical measurements, cone penetrometer data from the Apollo missions to say, you know, our soil on Earth matches their cone gradients on the moon. And therefore, to some extent, you've accounted for lunar gravity. So it's certainly, when we start talking about mechanically interacting with the surface of the moon, gravity can certainly not be omitted in terms of design. And so the previous slide was about reactions on the vehicle, but now we're only talking about half the equation. So like I said, GRC1 kind of attempts to account for the 1G, but a lot of simulants neglect it entirely. So your vehicle that you're testing may be 1/6 the mass, and it might be lunar appropriate in terms of weight, but the surface that you're interacting with is still under 1G, and there's really no way to avoid that, especially in full-scale vehicle testing. And so it's something that needs to be accounted for when you're analyzing your results. So like I said, we just did this whole V&V campaign for Viper in the GRC1 soil simulant, but it is a heavy consideration that, you know, the lab itself is still under Earth gravity. So we're looking to, you know, always keep that in the back of our minds. And at the end of the day, there's certain cases where there's not so much that you can do, but if as we continue to kind of look into these other techniques, is maybe we could, the idea of the scaling laws would be, can you reshape the wheel such that it would interact with similar actual terra mechanics in Earth gravity as it would on the moon, working on pressures and forces and things like that. So there are potentially clever ways to do developmental testing in that, but it's something that should always be considered. And then this is the last slide here. And I mean, this itself could be a whole 3-day conference on just simulants. But depending on what you're interested in, I mean, there's a whole catalog of simulants available to you. So in the Slope Lab, we have for our large sandbox, we need to fill 40 tons of soil in that in the sandbox. And so that alone restricts the available, you know, soils in terms of who can even produce 40 tons of whatever simulant. And then also, can we pay for 40 tons of that given simulant? Some of them are tens of thousands of dollars per ton, and they may not even have 40 tons available. So if you're looking for 1 ton or even 100 grams or something, just the volume alone that you need is going to determine the envelope of simulants that are available to you. You really need to mark down, like, what is it you care about? Like I said, we care about particle size distribution. We care about particle shape. I don't care about the magnetic properties when we're testing in slope. I don't particularly care about the optical properties. Depending on the test, I may or may not care about the abrasive properties when doing traction testing. So you really need to mark that, take a nice catalog of what it is that you're trying to test, and then that's going to direct your simulant choice. Because if you are testing with the incorrect simulant, your data may or may not be useful at all. So we're conducting testing right now that says, basically, we're using the soil simulants that we have available, and we're acknowledging certain things about those soil simulants, but we're just comparing the test against itself. It's not necessarily to achieve perfect lunar conditions. And so as long as you're clear about the scope of your test and the scope of your simulant use, there might be more options available to you. But these simulants can get incredibly expensive. There's, like I said, stuff can be $40,000 a ton for some of the really high fidelity ones, versus some of them maybe $100 or $200 a ton, or maybe you're just buying sand from Home Depot. So this is something that is, like I said, a whole talk in and of itself of how you choose this and what's appropriate for your testing. And so there is a website. I will drop it in the chat of NASA's putting together kind of a simulant library. And I believe they're noting common uses and stuff and availability of those given simulants. So that would be a good resource for anybody that's interested. And a last little bonus point here. Like I said, I was just emailing about some vacuum soil testing that we're currently doing. Into the previous point about vacuum, that alone is a whole test series as well. When you start vacuuming down soil simulants, you start interacting with water that may or may not be trapped in the particles. And so there are rates. We've published some stuff previously in our large scale chamber. It was published by Julie Kleinhens. You can start to, it appears to boil the soil, but what you're actually doing is you're interacting with the water that's trapped in the minerals. And so you can get these eruptions and boiling looking effects. And so if you care, like we do for our test, about, having a well-characterized soil preparation, if you start boiling and erupting within the soil, then you've kind of negated that soil preparation. So that's something that you need to take into account as you are pumping down your chamber. And so if people are interested about that, I can share some of the literature that's out there on that. And one final point, I didn't have info in my slides about this either, because I'm not as well read on it myself as I should be. But vacuum also affects mechanical characteristics within simulants. So it's something that I'm currently learning and reading about right now for my test setup. So another thing to consider with how vacuum, even as that one environmental change, really does kind of cascade and affect many different things. So that's what I've got.
Thank you. That was really good. You've got some questions in the Q&A to answer. Get ready for that.
Okay.
All right.
Perfect.
Thank you, Erin.
Yeah,
And
you bet.
our last panel member for the extreme environments is Charles Buhler, and he comes from NASA Kennedy. So I'll hand it over to him now.
Can you guys hear me? Is it working? Yes?
Yes.
Okay.
And your slides are flipped to the presenter thing.
How do I do that? Let's see. Oh man, how do I get it to the other screen?
If you go up at the top where it says display settings, sometimes it'll let you flip it there.
How about that? Is that better?
That looks great.
All right, thank you. Yeah, good afternoon. I'm Dr. Charles Buhler, the lead scientist of the Electrostatics and Surface Physics Laboratory here at NASA Kennedy Space Center. I'm going to talk a little bit about electrostatics as an extreme environment on the lunar surface. A little bit of reason why we do electrostatics at Kennedy Space Center. One of the worst disasters NASA has had in its history was 11 people being burnt alive due to a mishap, an electrostatic mishap, as people, workers, technicians ripped off plastic off of a rocket at the spin test facility out here back in 1964. So before that, electrostatics wasn't really addressed commercially. So Kennedy Space Center developed a triboelectric robot to try to capture and monitor and measure electrostatic phenomenon. This evolved over the years, and then in the late 90s, we formed into a research laboratory and made one of our first flight instruments that was slated to go to Mars, which is basically a triboelectric sensor to see how triboelectrics or electrostatics behaves in the Martian regolith that was developed here with collaboration with JPL, called the Mecha electrometer. So just a little brief history of the lab and what it is we do. We do electrostatics testing, solving problems for a variety of the agency programs, including the Artemis, but it goes way back to the Space Shuttle, Space Station. We've done some Hubble Space Telescope work, We work with SpaceX, Blue Origins. We really are the full-on electrostatics lab for the agency, but also customers. So we're going to talk a little bit about what it is we do and kind of how this applies to upcoming lunar missions. So what I like to do is to preface a lot of my talks with electrostatics on triboelectrostatics, because that is, in my belief, some of the electrostatics that's probably of most concern. As you're walking around in the high vacuum that we talked about, tribocharging against different materials, not necessarily dust, but even if you just tribocharge against yourself. So for example, this is a test campaign that we've done for the Hubble Space Telescope, one of the Hubble servicing mission. And the aim was to see, okay, what kind of triboelectric charging can you generate just by moving around, moving objects in high vacuum? Well, there are consequences to that. So as materials contact and they separate, they develop electrostatic charge. This happens on Earth. It happens every day. When you sit up from your chair, you walk across the carpet, you touch a doorknob, you get sparks. It's not uncommon to get to 20, 25,000 volts pretty easily due to just triboelectric charging. So what we can do and what we've done in the past is try to measure some of the fields that come out of triboelectric charging. So for example, for the astronaut suits, if they use ortho fabric or RTV or Teflon, the beta cloth is what they love to use. And that'll tribocharge against different materials. Could be metals, could be insulators, could be coated metals, could be other other spacesuit materials, or itself. You get some kind of generation of charge. And then what you'd want to do is, okay, does that charge actually discharge to something? What's interesting though, in high vacuum, unlike air, we weren't able to get brush discharges. So basically a brush discharge means, do I come by with a grounded probe and just discharge it? Can I just eliminate the charge that way? The answer is no, not with insulator surfaces in high vacuum. You can in air, but not in high vacuum. So it's a little subtlety there. But why do we care about this on the moon? So on the moon, you're going to be tribocharging. You're going to be tribocharging like crazy, whether it's a rover running around, you're going to be moving things, you're going to be moving hardware on the lunar surface, especially in the permanent shadow region. You're going to be especially worried about it. The moon is full of dielectric particles. So basically, I like to think of it as like a big giant ball of Teflon with chopped up pieces of Teflon on it. So you get the same primitivity of Teflon, roughly 2 to 3, your dielectric constant of your particles. The resistivity is quite high. They can be charged positive or negatively. You can't just assume one or the other. There's not really a zero charge on the particles. It's mostly bipolar. So you probably have equal amounts of both, not really zero. For design considerations on the moon electrostatics, we have to make note, the engineers have to know that the moon cannot be grounded. You can't electrically ground a habitat or a structure simply by drilling a rod into the surface. It's not going to work that way. There's just not a lot of current down there because the surface is very insulating. So that is something to consider, and there are ways to get around that. We'll talk a little bit about that, but essentially what you'd have to do is you'd have to attach to the space plasma. Now, I don't have a lot about the space plasma in this presentation. I apologize. There's a ton of literature on that, but essentially there is a neutralization up here that is available to you if you're exposed to the sun, about a microamp per square meter, roughly. It's a very dilute plasma. So don't make any illusions about that. Your tribocharging will dominate. It'll take some time for that charge to dissipate in the full breath of the sun. But even with that, you have to know that the Apollo astronauts, even with their suit, they were still tribocharged significantly enough to get dust to attract to it everywhere, even on their neck and armpits and their back. And that's because the surface is very, very dry. There's no moisture to allow charge decay like there is on Earth. This opens up the field of the possibility of very large electric fields being possible. So now our Earth breakdown, when we have a brush discharge or a spark, we know what kind of fields it takes for that to happen, whether it's lightning or whatever kind of spark that happens in the atmosphere, about 10 to the 6 volts per meter. On Mars, it's 100 times less. So it's easier to break down. You don't have lightning bolts. You have what's called a glow discharge. But on the moon, it's about 10 to the 8th. So that's limited by an effect that we call field emission. So basically, electrons have to spontaneously overcome the work functions of the metal to discharge. So It's a little bit interesting though. The 100 times higher E field is a 10,000 times potential increase in the energy of that discharge because it goes as E squared. Something to think about if we are going to have discharges as two materials come in contact or two large structures become in contact. You might have to think about how you're going to minimize those potential differences because there could be charge at different levels based on travel charging. I'll show a little example here with the astronaut walking. The polarization is probably something that really needs to be thought about. So essentially what that means is you'll have these electric fields, and even with no net charge on your surface, those fields can move that charge around and polarize it. It's basically what happens when you get up from your chair. Your clothes will be charged, but your skin is polarized. So the opposite charge will go to where you were sitting, and the like charges will repel as far as possible to get to your fingerprints or fingertips. And that happens here in the astronaut suit. So assuming all this MLI is conductive or the skin of the astronaut's conductive, you can get charge separation, even though the field that was created is way down here by his feet. The polarization effects transfer that charge and that current all the way as far as it can. So these are kind of things you have to think about a little bit when you're designing things in a very dry, high field environment. So one aspect of generating these fields is that it attracts dust. That dust is the great neutralizer. It's a problem, but dust has one job, and that is to neutralize electric fields, and that's what it'll do. So if you remove that dust, it will create an electric field, and vice versa. The dust is a problem. It's a dust accumulation. It's a significant problem and limited. One of the Apollo astronauts told us it limited to about 3 EVAs. Couldn't do a fourth one because of the dust getting into the mechanisms. A dust does have initial charges, which I'm not going to talk too much about in this group here, but there's a lot of science behind the initial charge of dust. The things that we like to look at is the electric fields that are created, are they creating any kind of incentive discharges, brush discharges, cone discharges? There are flammable gases present in some cases, depending on the configuration. There are tanks, there are fueling operations, there are digging, there's drilling. These things on Earth can and have led to incentive discharges. Like a cone discharge is another word for you heard a grain silo explosion in the Midwest. That's caused by electrostatics. The things you kind of have to look at and consider as you begin to scale up operations on the lunar surface. So we like to address dust. Our lab has been doing it for more than 2 decades. One of the ways we address the dust problems are EDS. If you're not familiar with it already, it's a active dust removal technology. Basically, you can put dust on a surface, and you don't want to use astronauts or gases or fluids or liquids to remove the dust. You just want to be able to push a button and just kind of get rid of the dust. And that's kind of what our electrodynamic dust shield does for glass surfaces. We can make it very large. There's me behind a solar panel EDS. We had a few flight versions of it using Apollo samples, reduced gravity flights. We make them for lenses and solar panels, thermal radiators. We're working on visors, doormats, spacesuits, a little prototype spacesuit, gaskets and seals. So this is one way that we address the dust issue. Keep people from touching it, grabbing the dust. We are having a payload go to the moon. One of the payload is our going on a CLIPS lander on the EDS, going to be demonstrated on a Firefly's Blue Ghost lander. This has been pushed to 2024, I believe. And what this device does is it generates and moves dust on a glass and a thermal radiator EDS. And then what we have is a kind of a neat reduster, which I'd like to show you. The reduster is a fun little experiment, but this will be jettisoned off of a leg, kind of a fifth leg. There's Planet Vac here, which is going to, as a way to use gases to inject and read and capture particles. Our system, we like to get rid of the dust. So one of the ways we don't know if we're going to get dirty on the moon, so we have to move dust around. You want to move dust, you have a conveyor belt system. You don't want to use mechanical parts and pieces or gases to do that. If you want, you could use reduster technology, which is based on the EDS technology. Kind of a neat little thing. We didn't know if we would get dirty being underneath the lander, so we're going to put our own dust on there. We're going to use our EDS technology to put dust onto an EDS so we can remove dust off the EDS. So showing that our technology can remove and add dust at will. So hopefully this will go to the moon in about a year, year and a half or so. And it works great in the air, it works great in high vacuum, but these are the kind of things you have to think about for sustaining a lunar base is how you move dust around, how you move regolith around. And then how do you get rid of regolith where you don't want it? This is a thermal radiator. So this thermal radiator has to remain white, otherwise it's not going to work as a thermal radiator. You want to move the dust, get it off, and then put dust back on at will. Oh, that's not the only EDS going to the moon. A couple of this is a very exciting experiment if you're interested in plume surface effects. The plume surface effects is when what we call the PSI is when the lander itself sandblasts the landing site. Very bad. So they want to capture that. They want to understand that. This is the EagleCam camera. So on the very first CLIPS mission, IM-1, this EagleCam CubeSat will be jettisoned prior to the landing of the Nova C lander on the lunar surface. And we'll film the landing of the lander as it happens. So that'll be the first ever third-person view of a spacecraft landing on an extraterrestrial entity, planet, the moon in this case. So what we can do is, what we have is a couple of EDSs on some of these cameras so that the cameras can remain clean, because this little box doesn't have any power. It's just going to be rolling around and bouncing around on the lunar surface. And from that, we'll get a little bit of a dust plume imagery and some PSI effects. So other dust mitigation technologies that we're working on are this surface stabilization technology. So you have this inflatable plastic, if you will, that adherent companies made their rigidization on command for structures, single part acrylic epoxy resin that can be sprayed onto a surface. So imagine a spray on tarp, if you will. A spray on tarp can be used to prevent the plume surface interactions. So the lander can land on the on a surface. It's a surface stabilization technology. The astronauts can walk on it. So if you make the landing site out of this material, you can choose when you want to get dirty versus when you want to play in the dirt, instead of having to deal with the dust issue. So these are some of the things we're thinking about implementing. We are going to develop ways, we have commercialized ways to electrospray the resin. The electric field of the environment, if we can measure it, we can actually electrospray it this way. If you're going to spray anything on the moon, you want to be able to control the spray through electrostatics. You don't want to just spray it. The gravity will just take it everywhere. It'd be very messy. So we electrospray it. Same thing we kind of do with powder coating, how we, it's how we spray paint cars and furniture and all that here on Earth. We want to do kind of the same thing with the lunar surface. And what's nice about this spray is we can actually make it conductive. So for 2 cubic feet by volume of this liquid, we can do roughly 1,000 square meters. So 1,000 square meter landing pad with 2 cubic feet, which is fantastic. Now, if that's conductive, then that can be a large enough structure to have the capacitance needed for a grounding surface. So 1,000 square meter structure could capture the radiation from the sun, the electrons and the protons, get you the current that you would need for a good grounding system. That's important for a lot of reasons, especially when you start thinking about planning a lunar base in a permanently shadow region for sure. So there are a lot of other projects. I don't have time to go into them. This is my last slide.
Yeah, go ahead. Sorry.
That's my last slide. We do work with the NASA Dust Standard group, where we have kind of standardized for the agency how we put a known charge per mass of a simulant in high vacuum, applied it to a test article. Should publish that quite soon. We're on to our 3rd simulant. You can see the error bars are quite small, very exciting. That's something that we're working on. We're working on helping with some of the modeling of the EVA suits, dust adhesion, dust lofting, tools for astronauts to use to remove dust from surfaces, all these things that that are important for, for the extreme environment that we're in. Anyway, that's all I had. Thank you.
Thank you very much. Now, you also have some questions in the Q&A, and I think we'll go ahead and answer those as you can over the next little bit. But I wanted to get Todd back. Can I get you back, Todd?
Sure.
Because, yeah, I wanted to ask kind of a more general question. Is are there any, when we heard from Alex, we hear, oh, this is kind of a guess, or we're still we need more information. Do you have any specific data or technology gaps that you see as a problem for being able to effectively do either the PSR or on the rim of this crater? What effects do you see being the biggest challenges, and do we have what we need, in your opinion, to get past them? We'll start with Charles. Oh, we cannot hear you. We can see you.
How about now? Can you hear me now?
There we go.
So yeah, I mean, for measurements, there's a lot of measurements that are needed for the PSRs, right? For the permanently shadowed regions on the leading edge, the leeway edge, the falling edge of the craters in terms of electrostatics. There's a lot of models and papers out there that describe how the heavier ions kind of deposit on the front of the crater, but as you get into the crater, the electrons kind of make it through, they're lighter, and they deposit on the surface. So for electrostatics, they're worried about that because it can build up, in some estimates, 4,000 to 10,000 volts or even higher. Those measurements probably should be done prior to walking into a crater to make sure that you're not stepping on a highly charged surface that you're going to discharge. So that's something that's of concern. There's a lot of theory. I'd like to see some more measurements done. But there's a lot more experts in that field. But that is something I would be interested in for sure. The initial charge would be nice to know.
And I think, to add to what Charles was saying at the beginning of his talk, because we work with Emily Willis here and the team that has created the so-called Disney, the Design Specification for Natural Environments, and they've been able to capture a lot with the charged particles coming in, the plasma environments, and so forth. From the Earth's like magneto-tail crossings, excuse me. But the point is that when she's asked about tribocharging, she's like, I don't know. I don't have it. It's so complicated. And that's what Charles started talking about. And that's a big one in my mind. We need a lot more information on sort of what is the typical, like if you are in sunlight, what is the typical charge through tribocharging that you will tend to adopt, the astronaut will adopt or the rover will adopt. And so those would be great measurements to have. So all of the electrostatics really on the surface of the moon or in a PSR or on a rim of a PSR are really, there's lots of models, but we need measurements because the models have a hard time dealing with all the different components, particularly all the different regoliths, regolith composition and so forth. So I think Charles' talk was great because it should list all of the electrostatic complexity out there.
Erin, and you?
In terms of how electrostatics affect what we've got going on in stimulants?
No, not necessarily. You can hit on it. The question was more of, with dealing with either being on the rim or being in a permanent shuttle region, are there design concerns? What's the number one design concern or data gap that you, in your opinion, what you do that we have there, and what would be the difference between those two locations?
I think the number one concern is temperature, frankly. I think that case number 2 offers, and it is maybe the simplest from a systems perspective in terms of traversals and things like that. But I mean, you're talking about designing literally every single component for continuous operation at 30 Kelvin, 35 Kelvin, which is unprecedented. I mean, most things aren't even operational for one cycle at 30 Kelvin, or 35, but let alone continuous operation for, I mean, ideally decades, right? Or something for a base, you're looking for multiple years and continued development and growth. So from that standpoint, I think that the most feasible from a technological development standpoint is maybe parking on, I think it was case 3 was the parking on a smaller crater, maybe nearby Shackleton, so you'd have eventual, or nearby a larger crater for eventual access to that. But I mean, I think there's a truly incredible amount to learn, even just from dipping into a couple feet of permanently shadowed region. something, I mean, things like we rely on a lot of compliant materials every day that we just kind of are neglected, and things tend to not be compliant the closer you get to absolute zero. So things like that, I mean, like astronaut safety in 35 Kelvin, the suit's materials, I can guarantee you, are not operational in the same capacity at that temperature. So I would say temperature and design of individual materials for even extended minutes, let alone hours or days in a permanently shadowed region, is an enormous technology gap. And then from the material development, you can start designing systems, mechanisms, subsystems in order to achieve those goals.
I know you were hitting on materials that we use every day, and kind of touching on Charles a little bit with charging. You know, I agree. We look at materials sometimes and don't take into fact that, you know, those properties change, their conductivity changes when it gets really cold. There's just things
Exactly.
that we don't really account for and we don't have the data for. So that's we hear that a lot about temperature, so I could agree on that.
Even
we are at
ice
yeah.
is not the same at those temperatures. So sorry.
Oh, no, you're fine. I wanted to see if any of the panel members had anything else they wanted to say before we head into our next break. All good? Oh,
I
Todd.
think we'll have a chance in our breakout session, right? So
Yes,
if we
we have
wanted to get
90
into some
minutes.
details, so
Absolutely.
so we'll reserve for that then.
Okay, and when we come back, go ahead and take your break, Charles. I don't want to take from your break, but if you could get to some of those questions in the Q&A, along with Erin and Todd, if some of them are for you guys. So we're going to take our 10-minute break. Is it 10 right now? I think it's 10 minutes this time. Yes. So we will start back at 10. Oh, I'm on the wrong time scale. 1:45. Or no, 1:55. Sorry.